So for this video, we're going to attempt to find the electric field using plane wave electromagnetic properties. So what we're given is we're giving an H field, and we're looking for the E field. So if we want to write the standard form for an E field, we can write E vector is equal to E naught vector, and then we can take this whole portion and we can move it to our electric field. The reason why we can do this is because the H field and the electric field should be in phase. They're not always in phase, but for this problem, there aren't any other parameters, so we can state that it's in phase. So we'd say sine 10 to the 9 t plus 3x minus 4z. So for a problem like this, we want to identify a few things. We want to identify what our k vector is, what our omega is, what our n is, and then we also want to solve for E naught. So how do we go about doing this? Well, we first identify what the k vector is, and we get that from these numbers, 3x minus 4z. So our k vector would be negative 3x hat plus 4z hat. All right. Now, you might be asking yourself, how did I find the k vector? Well, the k vector inside the sine function is what we call a wave function. And the standard form for a wave function, omega t minus kz and omega t plus kz, act very similar to a shift, such as f of x minus some value t. So, if we have a minus here, this behaves like a shift going to the right. So instead of going to the right in terms of position, we can say that our wave is traveling in a positive z direction. The same can be said for our plus here. It would be the opposite, so it would be going to the left, or possibly a negative z direction. To plot an f of x minus t is simply by shifting the value of that direction by t. So that same phenomenon gets applied to our wave functions. And that's why when we write their k vector, we use the opposite of the sign as observed here. So we have plus 3x and minus 4z, but for our k vector, we turn that into negative 3x and plus 4z. And it's only because we have a wave function that acts just like a shift. Now, we just have to find the value for n, and we get this equation, omega over k is equal to 10 to the 9 over 5, which is equal to c over n. We know what c is. The c constant is equal to 3 times 10 to the 8. So now we just solve for n. So now we get n is equal to 5 times 3 times 10 to the 8 all over 10 to the 9. And that gives us an n value of equals 1.5. All right. So now that we've found our n, and we've found our k vector, we can start solving this problem to find the E field. Our next step is to use the ratio of the E naught and the H naught to find eta. So we have E naught over H naught is equal to eta. And this eta right here is equal to eta naught over n. Our E naught divided by our H naught is our ratio for the wave impedance, eta. The wave impedance, eta, is equal to eta naught over n, is only true for non-magnetic material, which is what we are dealing with in wave propagation, unless we are explicitly working in ferrite devices. Eta naught is equal to 377. So this will always equal 377 for no matter what problem you're doing for plane wave electromagnetics. And we have our value of n, which is 1.5. So if we calculate this out, we get 251. And then we have to solve for E naught because we're doing electric field. So E naught is equal to 251 times H naught. Our H naught for this problem will be 0.01. So we just plug that in. 251 times 0.01 will equal 2.51. So we have our E naught now. Now the last part is we have to find E hat. E hat. The reason why we're looking for E hat is because on E hat, our wave follows the right-hand rule. So we can say that the E field is perpendicular to our H field, which is perpendicular to our K field. So we can say that K hat is equal to E hat cross H hat. So if we want to find E hat, we can say E hat is equal to our K values, which we know to be this K vector is equal to negative 3x hat plus 4z hat. We can plug our K into our E hat. So we would do 4x hat plus 3z hat, and we'd put that over the square root of 4 squared plus 3 squared. We use E hat to find the amplitude and direction of our E naught. So our E naught is the same thing as saying E hat, or a unit vector, times E naught. We use E naught is equal to eta times H naught. So by finding the unit vector E hat, and by using E naught from here, we can find the amplitude and direction of our E field. E naught vector is the same thing as saying E hat times E naught. So how do we find E hat? We do E hat is equal to 3x. Oh, my mistake. It's actually 4x plus 3z. And both of these have hats because they are unit vectors. Now for the bottom portion, we divide that by the square root of 4 squared plus 3 squared, and that gives us 4x hat plus 3z hat is over 5. All right, so now that we have our E hat and our E naught, we can add those to we can put those into our equation. So ultimately we get E electric field vector is equal to 4x hat plus 3z hat over 5 times 2.51, which is our E naught. And we write sine 10 to the 9 t plus 3x minus 4z. So our k propagation is the same for both the E field and the H field. And then we also know that they're perpendicular as well. So if we want to put this on a XYZ plane, we can draw it like this. We know that the H vector, or we know that the H field and the E field have to be perpendicular to one another, and those have to be perpendicular to the K, or the direction of propagation. So let me just erase all of this really quick. Move this up. If I were to draw this on a ZX plane, I'd have something that looks like this. The X direction, the Z direction. Right. So in order to find where the E field and H field lie on this ZX plane, we have to look at the equation that we have for the E field and for the H field. So the values in front of our sign here for the H field and E field will determine where they lie on this plane. So let's first look at the E field. For our E field, we have a 4x and a 3z, and both of these values are positive. So we can assume here from those values that E is being drawn in the first quadrant like this. Now let's take a look at the H field. Our H field right here has a value of 0.01 y. So it's constantly y in this problem. So because we can see that, our y will be into the page like this. So our H field is into the page. And lastly, we can look at K, which is the direction of propagation. So what we have for our K vector here is negative 3x plus 4z. So that puts us in the second quadrant, negative x and positive z. So this will be K, our direction of propagation for the wave.